Hey everybody, welcome back to our third video for lesson 2.2. We're going to continue the conversation of independent and dependent events. So if I'm dependent, that means something has already happened and I'm going to be impacted by it. This second event is going to be different because something already occurred. And that's called a conditional probability. Now we denote it as the probability of F is the event about to happen. This little line right here means a given. This probability is the one that has already occurred. The one that already happened. So when I move to dependent events, I'm still using the multiplication property. When I have these two events, I can look at them separately, E versus F, and I will multiply them together. But because I'm dependent, when I go to take that second probability, I have to consider the fact that E, the first event, already happened. Let me show you what I mean. What is the probability of drawing a king and then a queen without replacement? So these are dependent. When I look at the probability of getting a king and then a second card, a queen, right? Two separate events here. I can treat the first one just like any old find the probability of a king. And tells me to multiply. But when I go to look at the probability of the queen, it has to be given that the king is already selected. Because I didn't replace it, when I go to determine that second probability, I have to take into consideration that that king is already gone. So if I'm looking at the probability of the king, there are 4 of those out of my total. The first one's just normal. 4 kings out of 52 total. That tells me then, and tells me to multiply by. Well, now when I go back to find the probability of the queen, it has to be given that the king was already selected. In other words, when I picked up this king, when I picked up that one card, I didn't replace it. So now, how many queens are left over in the deck? Well, thankfully, my queens didn't change. I still have 4 queens. But what did change is how many total cards are left after I picked up that first king. Well, now there's only 51 cards in the deck. That's what we mean when we say dependent probabilities. I have to remember that that king is gone. So there's still 4 queens in the deck because I didn't pick up a queen. But when I removed that king, there are only 51 left over. And we're ready to multiply. Let's go ahead and reduce this one by 4. 4 divided by 4 is 1. 52 divided by 4 is 13. I don't know that those can reduce, right? They're not both even. So let's just leave it and multiply. 1 times 4 is 4. 13 times 51 is 663. I can leave it as that fraction, or I can give it as a decimal, 0.006. Whoops. So with the dependent probabilities, I still just can remember that and tells me to multiply them together. But I have to take into consideration that second one, assuming the first has already happened. Let's do another one of these. Assume that there are 17 men and 24 women in the Rotary Club. 2 members are chosen at random each year to serve on the scholarship committee. What is the probability of choosing 2 members at random, the first being a man and the second being a woman? Are these independent or are these dependent? Y'all, people are pretty much always dependent. Because what happens is I can't have one person be in both roles. People don't get replaced like a card in the deck. So these are dependent still. If I'm looking at the probability of being a man first, and then selecting a woman second, I can look at those separately. Find the probability of just selecting a man, and tells me to multiply by the probability of selecting a woman, given the man is already chosen. So in the very beginning, if I'm just looking at my men, that's just the number of men out of my total. So how many men are there? 17 out of, well, I don't know the total yet. Let's see. 17 men, 24 women. That is 41 people. So originally, there are 17 men that I could choose out of the 41. Friends, I am not picking up all 17 people. I choose one of them. What that means is when I choose one, now there's only 16 men left. So there's only 40 people left to pick from. I have to take that into consideration when I move over to find the probability of being a woman. So when I when I determine the probability of selecting a woman. So for that probability, on top would be the number of women that are left to select from out of the total number of people left. Well, my women, those haven't been impacted, right? I still have all 24 women to select from. Out of my total, now there's only 40. Multiplying those together. Keep in mind, 17 is prime, so I cannot reduce that first one. So I have 17 out of 41 for the first fraction. Let's see, the second one could probably reduce by 8. 24 divided by 8 is 3. 40 divided by 8 is 5. Friends, if you are not good at simplifying these fractions, then don't simplify them. Multiply them straight across the top. Multiply them straight across the bottom. So, actually, let me pause for just a minute. Let me finish this one that we're dealing with, and then I'll show you what I was talking about. After we reduce here, 17 times 3 is 51. 41 times 5 is 205. If you want that as a decimal, it would be 0.249. If you are struggling with reducing, then back up and multiply first just straight across the top. 17 times 24. That's the top of my fraction. On bottom, 41 times 40. That's the bottom of my fraction. You are allowed a graphing calculator on here. Notice that if I take top and divide by bottom, it moves straight into that decimal, but I can hit math. See a little arrow that says fraction? And it tells me the reduced fraction is 51 out of 205. Use the resources you've been given. Let's do one more of those. Still looking, 17 men, 24 women. I'm still selecting people for a committee. This is still dependent because I'm not going to select the same person twice. This time they want to know the probability of choosing 2 members and both being men. So what's the probability of choosing a man first and a man second? The rule says I can look at the probability of just the first man and tells me to multiply by the probability of the second man given the first has been selected already. So in the very beginning, if I want to know the chances of picking a man, I just have to remember there's 17 men. Those are my possible options. Out of, remember my total, 17 plus 24 was 41. That first probability is not changing because it came first. However, I then have actually selected one of the guys to sit on the committee. Once I've selected that guy, I'm not going to choose him again. So there's only 16 left in terms of my options. Means there's only 40 left in terms of my total options. So when I go to look at this second man to be selected, now there's only 16 left out of my 40. Notice how that changes. I'm going to go and do this one as if we're struggling to reduce. That's a very real thing. Multiply straight across. 17 times 16 is 272. Multiply straight across the bottom. 41 times 40 is 1640. And then let's let our calculator do some work for us. Math fraction. It gives me a result of 34 out of 205. Which if you divide as a decimal would be 0.166. Final answer. Whew. All right, friends. Independent versus dependent. Let's stop this video here. In the next video, the last video for this lesson, we're going to focus in a little bit more on that conditional probability and have one more example that's some special cases.